So this video is literally going to be me going over the test review quickly because I know you guys have not a lot of time. But anyways, so the P sublevel represents I would say that it would be a dumbbell shape. So it represents the dumbbell shape. Okay, so what I would suggest you reviewing it for this is S, the shape is the sphere, remember? P is the shape of that dumbbell, that red thing that I showed you in class. D is a shape of two dumbbells, basically. Could call it clover. And then F would be the clover times 2, and we kind of will represent that with the dots. Okay, so that's it. So the P sublevel resembles the dumbbell shape. All right, next question. Atoms that have the same number of electrons are, you guys should know this, we've done many examples lately, is isoelectronic. Okay, so atoms that have the same number of electrons with each other are isoelectronic. So just because it has a number of electrons as a noble gas does not mean that it is the same atom. Remember, there are differences such as protons. The number of protons never changes. Okay, so just because the chlorine ion will have the same number of electrons as argon, that doesn't mean it is now argon, because it still has the same amount of proteins as chlorine. All right, next question. Atomic orbitals can hold 2 electrons at most, and they must have opposite spins. So that is known as the Pauli exclusion principle, or just P-A-U-L-I, Pauli exclusion principle. Okay. So these are just rules that you need to know. They're in your PowerPoint. If you want to review it, I wouldn't spend too much time on those. But a method that indicates the arrangement of electrons in a particular element. So if you'll think of what we've literally been learning for the last many weeks, it's electron configuration. So electron configuration is actually how we arrange electrons. It's basically the same word. So when we're arranging electrons, we're basically doing electron configuration. Sorry guys, I've been grading lab reports all day. Configuration. All right, electrons closest to the nucleus of the atoms are blank in energy. So we'll say this is the nucleus, okay? And then we have this principal energy level, this energy level, this energy level. The electrons here are much lower in energy than the electrons here, and even lower in energy than these. So these are high energy level electrons compared to these, okay? So electrons closest to the nucleus of an atom are lowest in energy, okay? So the N equals 2 energy level contains these sublevels. So the N equals 2 energy level contains these sublevels. So if you'll remember, let me zoom out. Okay, so N equals 2, so N equals 2, so this is N equals 1, okay? N equals 2 is this second line right here. So N equals 2 will be including the S sublevel, and it'll include a P sublevel, okay? So if for a question like that, if it asks for like the third, you have S, you have P, but in the third sublevel, you also have a D, okay? So the answer is the N equals 2 energy level contains S and P. Should I zoom in? Okay, yeah. All right, so the next question, the S sublevel resembles this type of motion or shape. So all we have to do is really reference what we know here. S resembles a sphere. Okay, next one, elements lose or gain electrons to become like this group of elements. Hopefully you guys know this already. The answer for that one is going to be noble gases. So they want to be like the noble gas. The n equals 4 energy level contains these sublevels. So n equals 4. Of course, we're going to include the f orbital this time. Okay, so n equals 4. So if you'll remember the periodic table I made you color, the S block starts at 1, P block starts at 2, D block starts at 3, and the F block starts at 4. So the fourth sublevel will be these. So it has an S sublevel. 4P is here, so it has a P sublevel. 4D is here, so it has a D sublevel. And don't forget that F actually starts with 4. So it has an S, P, D, and an F sublevel. So the n equals 4 energy level, okay, the n equals 4 energy level contains S, P, D, and F. Okay, number 10, blank, a blank is the average distance of the electron to the nucleus of the atom. So this one is, so the average distance from the nucleus here to the next energy level, okay, that's called the principal energy level. Oh, sorry, principal energy level, okay? All right, next question. Write the complete long form electron configuration and include how many valence electrons there are for each of the following. So all we have to do is do the complete electron configuration and find its valence electrons. So I'm going to zoom out a little. I'm going to zoom out a little bit so I can bring this guy in. All right. So, yeah. Right there. Okay. So we're doing Ga. Ga is right here. It's gallium, not Gallia, but gallium. And it ends at, this is 2, 3, it ends at 4p1. So I'm going to do the complete long form electron configuration. So you first always start here for long form, and it's 1s2. The helium's actually over here in the s block. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, don't forget that d's start with 3, 3d10, then we're back at 4p1, okay? So I'm just going to write that down real quick. You guys should probably be like, this should be very easy for you at this point, hopefully. If not, you're a little behind. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. I think it stops, so 3d10, and then it stops at 2, 3, 4. 4, let me make sure I'm on the actual thing. It stops at 4p1. So that's the long form electron configuration for gallium, long form. Okay, and then it wants to know valence electrons. So with valence electrons, you're going to look at the highest principal energy level. The highest principal energy level is going to be, let me use a different color. So principal energy level, guys, these are represented by these numbers right here. So we're going to look at all these numbers and we're going to pick the one that's highest. So that's easy, right? We see that 4 is the highest out of all of these, okay? So we're going to pick 4 and then we're going to look up here, and up here it tells us how many electrons. So these numbers represent number of electrons. So there's 10 electrons in the 3d orbital. So anyway, so we're going to just literally add up the electrons in that fourth energy level, and it's 1 plus 2, and that's going to equal 3. So valence electrons will equal 3. Okay. All right, so we're going to do the electron configuration for iridium and then find its valence electrons. Sorry. Okay, so iridium is, let me zoom out. Okay, oh my gosh, why do I keep doing this? Okay, so iridium is here, okay? So first we're going to do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then we have this whole f orbital. So 6s2 to 4 14. Then we're going to do the d orbital, which this is where it gets weird, but bear with me. So we have 3, 4, 5D, 1, 2, 3, 4, 5, 6, 7. So the end will be 5D7. You count this block, okay? So the electron configuration for iridium will be, okay, 1s2, I'm going to write it smaller, 2s2, 2p6, 3s2, 3p6, 4s2, 4p, oops. Okay, 1s2, 2s2, 2p6, 3p, 4, this is 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and so we are at 6s2, so 1, 2, 3, 4, 5, 6s2, so we've done this one. This is where the weirdness comes in, the F. So you're going to go 4f14. There's actually 15 in there, but remember what happens with the d orbital. So 4f14, and then we go back up. So this is the third, fourth, fifth energy level. So 5D, 1, 2, 3, 4, 5, 6, 7, 5D7. So 5D7. That's our long form electron configuration and valence electrons. So I'm going to write right here, valence electrons, okay? So valence electrons, again, I'm going to look at the energy levels, which are represented by these numbers at the beginning of each little 3-section part. I'm sure they have a name for it, but of course I wouldn't know. Okay, so the highest number that I see is 6, okay? So the 6th energy level has only 2 electrons, so valence electrons equals 2. Easy, easy, so easy. All right, write the orbital notation for each of the following. Be sure to label your sublevels. Okay, so orbital notation, guys, in class I've taught you in circles, in circle form, but you can also do it in line form, as you have seen me do with the quantum numbers. So the first question's asking about the orbital notation for oxygen, okay? So basically, I like to write the electron configuration first. So 1s2, 2s2, 2p4, 1, 2, 3, 4. So that one's going to be quick and easy. So it'll be 1s2, 2s2, 2p4. The orbital notation, so S, you guys know, has only one sublevel. S has one sublevel, okay? And then P will have 3. So 1, 2, 3. Okay, this also we've learned, okay? Circle, circle, and then circle, circle, circle. Either way, I don't care, okay? So then you're going to do orbital notation, that's the arrows, okay? So here, the S sublevel is filled first, or like this, whatever way you like. Okay, the second S sublevel here, okay, or circles, whatever. Then the third sublevel is filled up until we have 4 electrons, and those 4 electrons will be put here or here, okay? So you fill it up, 1, 2, 3, 4. Okay, you can do it here, 1, 2, 3, 4. Okay, so that's the orbital notation for oxygen. Now we're going to do scandium. It's right, oh, you can't see. It's right here. So again, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, what was it, 1, 3d1. Anyways, so then you just draw your orbital notations. I'm going to go ahead and do circles because that's what I've been doing in class. I like the circles better. I don't know why. Maybe because that's how I was taught. But S will have 1 circle. The other S will have 1. P will have 3. And I like to kind of let them touch a little bit. S will have 1. P, 3. 3. S will have 1. D will have 5. 2, 3, 4, 5. That's going to bother me. I'll make it a really fat circle. Okay. All right. So now we just fill in the electrons. These 2 electrons are going to go here, up and down. These 2 electrons here, up, down. These 6 electrons will go here, up, 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 down, down, down. And you kind of get the idea. Up, 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 down, down, down. Okay. 4s2, up and down. 3d1, you'll just have 1 right there, okay? So you'll only have 1 electron in the d orbital. Got it? Done. Okay, so use noble gas abbreviations to write the electron configuration for each of the following. So noble gas abbreviation to write the electron configuration for each of the following. Oh, so you'll also see like short version, abbreviated version, noble gas abbreviation, noble gas configuration. Something like this. If it's asking for a shortened version, all you're doing is the noble gas version. So we're doing that with, okay, sorry, there's boys outside being crazy. With RA, okay? So RA is right here, okay? So instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, blah, 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 all the way over and over and over, you would just literally go up, over, and you're at radon. So here's your most previous noble gas. Not the closest, but the most previous. Okay, so that's radon. So I'm going to put that in brackets here. Rn. And that assumes when you write this, it'll assume 1s1, 2s2, blah, 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 over and over. You get it, okay? So instead of saying, like how to get to the Acropolis, instead of saying, okay, first you must get out of your seat, walk to the Ms. Passon's classroom door, and then turn right, and then walk straight until you come to another set of doors, and then you walk out of the academy, and then you kind of turn a slight left, and then you keep going until you hit the gates. Instead of starting from the very beginning, you can say, okay, so do you know where Monostoraci is? Yes? Okay, so then it's this way, and it's a shortened version of like a set of directions or instructions. So RN, so this is our abbreviation. So the RN in brackets takes the place of all of this mess, okay? So now we just do, I think that's 7. 1, 2, 3, 4, 5, 6. So then it's 7s2, because that's 7s1, 7s2. So that's it. 7s2, okay? Now let's do Sm, which is in the f orbital, okay? All right, so again, we're going to go, so Sm is right here. So really it's right in this one. So the most previous noble gas will be up and to the right, so that'll be xenon. So in brackets, you're going to put Xe, okay? Then you're going to, go xenon. Then you're going to go down here, which is 6s2, and you're going to write it. 6s2, and then you're going to count 1, 2, 3, 4, 5, 6. Okay, so you count the first one. So it's 1. So 6s2, and then here it's 4f 1, 2, 3, 4, 5, 6. So it's 4f6 at the end, right? Oop, there goes something. I don't know what it was. I forgot what I said. Oh, 4f. 6, 4, 6. Okay. Oh, you can't see. So that's the answer. That's the noble gas abbreviation of that. It's very easy. Very, very easy. Okay. Next. That's okay. Oh, dang it. That paper was my second page of my review. Okay. Next page. Okay. I am so unprofessional. Okay, write the long form electron configuration for each of the following ions and tell which noble gas each is isoelectronic with. Okay, no big deal. A lot of words, but no big deal. So what it's asking for, long form electron configuration, that's the very first thing we've learned, but it's an ion, so that's where it's weird. And tell which noble gas each is isoelectronic with. So what we're gonna do, I'm going to go ahead and write the electron configuration. I would suggest going, on one of the previous videos if you're still stuck on it, but I'm going to do it quickly. So electron configuration, how I solve these problems is I first do it for the neutral atom. So first I'm going to do it for just iodine, okay? So neutral. So 1s2, it's pretty far down there. It goes down to 2, 3, 4, 5, 5p5. So 1s2. 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 1, 2, 3, 4, 5p6, 5p5. Okay, so that's the electron configuration for the neutral element of iodine. Okay, so of iodine. Now we have a -1 charge. So if I have a -1 charge, please again, do not get the charge confused with the number of electrons. So these are the number of electrons. These are not charges. So please don't be confused with that. Anyways, so those are electrons. This is a charge. This is a charge, okay? So that charge means I have one extra electron, so I need to find the highest energy level and add the electron to it. In this case, the highest are these two 5s, but P is higher energy than S, so we're going to add one electron to the 5. That's a plus. I don't know if you can tell. I'll make it really big. +5. +1, I mean, okay? So then the electron configuration, it's the same thing. Everything's the same. So I better do it. 1s2, 2s2. 4d10, 5p6. So then this right here is the same, so it's isoelectronic. So this is the long form of I-1. So of I-1, that's the long form electron configuration. And then to find out what it's isoelectronic with, you're going to add all of the, you're going to add all of these electrons, okay? So you're going to add 2 plus 2 is 4, minus 1 is 3. So you have 4, 6, I'm sorry, 2 plus, so 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 49, 50, 51, 52, 53, 54. So 54. So if you look on so you just look on the periodic table, and the place that has the highest, I can't think. My camera did something weird. Okay, so you look on the periodic table, and whoever has the same number of electrons, that's who you're isoelectronic with. So that's 54, that's xenon, and that's what you're going to write for your answer. So here is xenon. Okay, calcium plus 2, okay? Calcium is right here, so that's going to be easy. That's literally going to 1, 2, 3, 4, 4s2. So that's going to go, so I like to do the neutral, like I said. Calcium, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So now I do the calcium ion, which is 2 plus. So if it's 2 plus here, I'm going to find the highest and add, I'm going to subtract 2. So then my, that actually kind of goes away. So it's 1s2, 2s2, 2p6, 3s2, 3p6. And that's my electron configuration for calcium 2 plus. And it's isoelectronic with, let's add it up, 2, 4, 10, 12, 18. Let's see who has 18 electrons, just like my ion. That happens to be argon, and that's my answer. Argon. Got it? Okay, so I think I can skip this one. It's literally the same thing. Okay, let's go to 15. This right here is where you guys kind of get confused. So we're looking, it wants us to identify the elements, ions, based on their electron configuration, orbital notation, and their overall charge. This one's going to be easy. It is neutral. So we just look here, 3p5. Let's find 3p5. That's 2p6. 3p1, 2, 3, 4, 5. And the answer is chlorine. Okay, so chlorine. So make sure you write Cl, but no charge, okay? There's no charge. So whatever this one is, it's going to have a -1 charge. Whatever this one is, it's going to have a -3 charge. Whatever this one is, it's going to have a +1 charge. Whatever this one is, it's going to have a, you guessed it, +3 charge, okay? So technically a -1 charge. So this is going to be somewhere here, because this is -1 charge. But that doesn't matter. We don't have to know that yet. So anyways, we look at 3p6. So whatever this ion is, it is 3p6, and if it's a -1 charge, that means it had to have gained 1 electron to be this electron configuration. So that electron configuration, 3p6, is going to be to 3p6. So that's argon. So who on this periodic table would have had to gain 1 electron to become like this? That would be chlorine. Chlorine has 17 electrons. If it gains 1, it becomes like argon. So it's going to gain a -1 charge. So it's going to be chlorine with a -1 charge, and that's the electron configuration. Next, we're going to do, so it looks like it's same, so 3p6, so somebody's going to be like argon, but instead they had to have gained 3 electrons, because it's -3 charge, it gained 3 electrons. So somebody had to become like argon. They had to gain 3 electrons, so 1, 2, 3. So phosphorus, okay? If phosphorus gained 3 electrons, okay, 1, 2, 3. So it gained 3 electrons and it became argon. So that's phosphorus. Easy, right? Okay, next, the +1 charge with 4p6. So let's see who's 4p6. That's 2, 3, 4p6. So krypton. We're looking at krypton with a +1 charge. So somebody had to have lost an electron to become krypton. We're not going this way because all of these guys have to gain electrons to be like krypton. So we're going to go down here. So if let's see how many electrons they had to lose. They had to lose 1 electron. So it's basically rubidium. Okay, so rubidium, if they lose 1 electron, so rubidium has 37 electrons. If they lose an electron, they're going to be like krypton. Okay, so our answer is rubidium, Rb. B-R-B. Okay, all right, and then this one, I think I've done this one in class like every single time, but somebody had to have lost 3 electrons because now they are now 3+ charge. So somebody lost 3 electrons to become like this, and just that circle with the X, that means there's 2 electrons in there. It's just the same as doing that. Okay, all right, so somebody with a +3 charge becomes 1s2. So 1s2 happens to be helium. So who had to gain, somebody lost 3 electrons to be like helium. So here, this guy had to lose 1 electron to be like helium. This one had to lose 2 electrons to be like helium. And boron had to lose 3 electrons to be like helium. So the answer is this.